morning, good afternoon, wherever you may be in your day. Thank you for choosing my general chemistry part of your day. And so endeth thermochemistry videos. So, now we're going to talk about how do we use entropy, second law of thermodynamics, and the idea of free energy. So, I might as well start with the second law of thermodynamics, which in its most simple sense is that the entropy of the universe is always increasing, or any changes in entropy associated with the universe will be greater than zero or a positive value. Remember, entropy is dispersion, randomness, chaos, nature. And again, think of the universe and the whole idea that the universe is expanding. So, changes to the system plus changes to the surroundings equals the universe, so that's also got to be greater than zero. And I pose a question to you all. We all know hydrogen tends to be a diatomic gas, which maybe we haven't thought about what that means, but it means if I take a hydrogen atom and another hydrogen atom and I react them, I will get H2 gas. This will happen naturally and on its own. This is something that will happen within the universe, which means it should conform to the second law of thermodynamics. So my question is this real? Did I just lie? Did I just violate it? Because if I look at this, I know in the last video Dr. Wergo said delta S was essentially the same as delta N gas. And in this case, I have one gas molecule forming from two, and I know 1 minus 2 is a negative number, and this is negative. Holy cow, this is negative. That's positive. You just blew my mind. But not so fast, my friend. We're in chemistry class, so of course we care about the chemicals, and we're looking at the chemicals, but we kind of ignored, the vast majority of the universe, the surroundings. So what's going on with the surroundings, and how can we give the surroundings more entropy? We can give the surroundings more entropy while not actually changing the chemicals that it's made out of. Out of that last video, what was the one thing we talked about that didn't need to change the identity of the chemical? I gave that example of water at 35 degrees Celsius and water at 10 degrees Celsius, and the higher the temperature, the higher the intrinsic entropy. So how do we make the surroundings have more entropy? We make them move faster. We give them more kinetic energy. That is a measure of temperature. We radiate heat. We might even call that an exothermic reaction. So bond formation, if you're actually going to form a stable bond, if you're forming that bond, you're creating localized order, which violates this. So to create that localized order, we have to create global chaos or disorder around it. So there's always a price to be paid. We create a little bit of order, we have to create more disorder around it. So how do we do that? We make an exothermic bond. The stronger the bond, the more exothermic it is, the more it vibrates the particles around it, and the more entropy they have, satisfying the second law of thermodynamics. So what I want you to remember, and a lot of times this gets muddled, when you get out of the physical sciences, the way that the energy exchange gets simplified down to kind of avoid really delving into thermodynamics, sometimes causes some real misconceptions. So when you form a bond, it gives off heat energy. It is exothermic. And because of that, and the entropy of forming that bond is going to be negative. The exothermic event will make the surroundings positive and balance it out. Bond breaking is going to be the opposite. You have to input energy in to break a bond. And where does this misconception come from? A lot of times we talk about ATP as being stored energy. But it's not stored enthalpic energy. It's not heat energy. We have to put heat energy in to break off that phosphate. Once we break off that phosphate, all those negative charges, remember phosphate's the only polyatomic with 3 negative charges, and then we put 3 of those things together, that's not real likely. That's a very, very low amount of entropy. Pop off one of those phosphates, those negative charges run away from the negative charges it left behind as fast as humanly possible, or diffusion controlled if you prefer, and gives off a large entropy increase, and that's that's the energy in ATP. So these are really at odds, right? One of these is helping and one of these is hurting in both cases, satisfying the second law of thermodynamics. Which means, and we already know this intuitively, not every atom is going to form a stable bond with every other atom. We talk about the noble gases, for example. So these are kind of at odds with each other, and I'd like to delve into this a little bit more in the next few slides, but I do want to just point this out. Bond formation is always exothermic. Bond breaking is always endothermic. They can be, both of these can be either exo or endogenic, which talks about the overall satisfying of the second law of thermodynamics. So just if you ever get a little bit confused or it seems like you're hearing something in biology that's different than physics, it's so subtle, very, very subtle, what comes after the exo and the endo. All right, let me define a term, then we're going to roll all this together. So the term I want to define is Gibbs free energy, a lot of times just called free energy. If you're wondering why free energy would be a G, it's because it's after Willard Gibbs. You might find this interesting. The first PhD awarded in the United States was to Gibbs. So we did a very good job. We picked something very famous and very useful. So good job by us. I believe it was out of Yale, if I remember correctly. And free energy was defined as the maximum energy available to do work with, or to do stuff with. This is energy we can use to drive things, going back to that ATP idea. Okay, so this is really the exogenic, endogenic idea. So if delta G is negative, this is energy we have that we can apply to something else. We can use to fuel another reaction. This is something that will happen on its own. I like to think given infinite time, the end of the universe, if we wait long enough, this will be a spontaneous process. For example, diamonds should turn into coal, but again, I don't know how long that takes, billions of years, hundreds of billions of years, I don't know, you don't really have to worry about it, but given infinite time, that's a spontaneous process. If it's positive, this means non-spontaneous, and what that word means, technically is, this is something that cannot occur without the input of external energy. So usually we say spontaneous means it'll go, non-spontaneous means it won't go, and again with the huge caveat of without external energy. So what do I mean by this? Have you ever taken a shower on the second floor of a building, in your house, in your dorm? Sure. Have you ever seen water just levitate out of the river or out of a lake? No. Why? Because water going away from the center of the earth is non-spontaneous. But if we put pumps in, if we use electricity, we can input enough energy for that to occur. So again, I don't want you to think these things are impossible to occur. They just can't happen without that outside input of energy. All right, so let's take a closer look at the second law of thermodynamics and put all these terms together. So the change in free energy is equal to the change in enthalpy minus the temperature times the change in entropy. So again, this is our measure of spontaneity. Negative is good, it will go. Positive is bad, it will not happen. So we want this to be negative. So when thinking about this, we want this to be negative. And then we have the enthalpy, which is basically our heat flow, and we have entropy, which is disorder. But we do have that negative sign out front. So let's just start positive and we'll go negative, because chemistry is a happy, positive place. Didn't think I forgot that, did you? So let's say free energy is positive. A reaction that will not happen. It is unfavorable at all temperatures. Okay. At no temperature is it favorable, or at all temperatures is it unfavorable, depending on the verbiage that you have in, say, a word problem or a question in the book. So if delta G, we want that to be positive, what would this value have to be? Well, this equals that, so the sign should match. So we'd want a positive enthalpy change. So it'd be like bond breaking. Bond breaking is more important than bond forming, for example. And then there's a negative here. So that means we want the opposite sign for entropy. So positive times a negative gives me a negative. So we want a negative entropy change. So this would be something that creates order or destroys disorder. Bond breaking is more important. Somehow we break bonds and we order things. If you can do that, that's a reaction that's never going to be favorable. Okay. We can do the flip side, and all the flip, if this is positive, positive, negative, then negative, negative, positive makes sense. And this is something that should always be favorable. Be favorable at all temperatures. So if it's exothermic, and somehow we can create disorder, if we can do those two things together, wonderful, fantastic. So we're bond formation, and somehow the bonds that we're forming are stronger than the ones we're breaking, and we break up a bigger piece into something smaller. That's something that's going to be favorable at all temperatures. Okay. So key here is when the temps, when they're competing, positive, negative, negative, positive, when they're opposite, that's going to be an all or none situation. Just look at the H. We want that to match. Delta G, positive, positive, negative, negative, and don't worry about this. Just realize that they're the opposite. Now, what gets really interesting is when they match. Positive, positive, or negative, negative. Now they're competing against each other. And what's our swing vote? What's going to determine who wins is going to be the magnitude of the temperature. Some things this temperature switch is room temperature. Some things it's, hotter than the sun. And some things it's, 1 degree Kelvin. I'm going to leave the math out of this and save it for Chem 102. But conceptually, we're just going to say high and low temperature, or higher or lower than the swing point. So let's take a look at positive and positive. This is hurting us. This is helping us. So this is what we want to maximize. We want to maximize this term. We want to multiply it by something really big. So this is going to be favorable, positive, positive. And this works out nicely. Positive, positive, big. Negative, negative, little. So if it's positive, positive, we want high temperatures. And if it's negative, negative, we want low temperatures. And again, this is bond breaking. So breaking bonds is better at high temperature. Forming bonds is better at low temperature. What does this look like in practice? Let's take a reaction and see what we can delve out of it. 4 iron metal plus 3 oxygen molecules forms 2 iron 3 oxide solids. And we want to estimate this. So is delta H positive or negative? Ha! I see plus oxygen. I know that's combustion. I know that's fire. I know that's exothermic. Boom. All right. Delta S. Dr. Wergo said change in moles of gas. So I got 0 gas here, and I start with 3, so my negative, that's negative. Negative 3 is a negative. I got negative and negative. And what's this tell me? That was L1. It's positive, positive up, negative, negative down. Not the greatest way to learn, but, it works. And this will be spontaneous or favorable at low temperature. If we heat this up enough, we'll drive off the oxygen and we can get metal. And then, now we're starting to talk about like smelting process, things like that in the opposite direction. And delta G here again, this is really tied into this. At low temperature, it would be negative, and then at high temperature, this would be positive. So hopefully that makes sense. Let's do 2 more quickie examples. What if it was a picture? Oh, I missed all these little circle atoms. Oh, look at them. Hello. We can do the same thing. Let's just start with delta H. So over here we have atoms. Over here we have molecules. Clearly we have done what? We have formed a bond. And I remember from 7.5 minutes ago, that means exothermic. How about the entropy? Dr. Wergo said change in moles of gas. We just did that like 29 seconds ago. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Boy, Dr. Wergo's not very creative. He did another example that was all negatives. Oops. It's okay. They're both negative, so it would be, again, same conclusion. It would be favorable at low temp. And at low temperature, delta G would be negative, and at high temp, delta G would be positive. What if it was in sentence format? Oh no, we didn't get a reaction. Such as ammonium chloride dissolves in water and the solution gets cold. Estimate the values, positive or negative or 0, for delta H, delta S, and delta G. You know what the easiest one to do with these types of problems is always delta G. Because it says what? Dissolves. That means it happened. We didn't do anything crazy. It just dissolved on its own. It's spontaneous. We know delta G has to be negative. So easy. The temperature got colder. Temperature went down. That is an endothermic process. Delta H is positive. And then if that's the case, entropy has to also be positive. Or you could think of a crystal, a solid, very ordered, going into aqueous ions, fairly disordered. So we get positive, positive, negative here. This is something that would be spontaneous at high temperatures. And currently we would consider room temperature a high temperature because the reaction does happen, it dissolves. Hopefully this made sense. I look forward to seeing you in class. Have a fantabulous day.